Okay, I think we are live now, so we'll get started. We're just going to go through the normal protocol of hopping and doing Anki first, and then we will go for going through as much of the exam as we can. We'll see. Hopefully, I'm able to. So I know there are a few of them that are going to be quick to do, and so I am excited about the possibility of working through more than I have in the past of the exam. I will be going through the rest of the like function slash the trigonometry functions. So there is that. Okay, so I guess we'll get started. So if you can't find a limit, normally you can manipulate the function algebraically such that the limit appears. This would be like a sort of a in the case of a whole discontinuity. The Pythagorean identity is cosine squared, or sorry, sine squared theta plus cosine squared theta is 1. Okay. Nice. U substitution is the reverse chain rule, and this is where we take an integrand that is in the form of f prime of x plus, or sorry, f prime of x of g of x plus g prime of x, and bring it to its f of x, f of g of x. The U substitution is the process that we use to go about it. Apparently it's simpler. Tangent secant. Okay, so tangent secant Pythagorean theorem would be an alternate form of the tangent secant Pythagorean identity is an alternate form of the main Pythagorean identity. So this one is tan squared theta plus 1 equals secant squared theta. And it's derived through sine squared theta plus cosine squared theta equals 1. You get this by dividing cosine squared theta. Okay. The Leibniz is the rate of change one, so it'd be dy over dx, and then the Lagrange notation is the prime notation for derivatives. Let's see. So dy over dx. Yep. Leibniz, focus on the rate of change. Perfect. The cotangent cosecant. Let's see what this one is. It's 1 plus cotangent squared equals cosecant squared by dividing by sine squared theta. Okay. An integrand is a function that you are going to integrate. Wait. Yeah. The double angle formula for sine, I'm not sure. The formula is 2 sine of 2 theta equals 2 sine theta times cosine theta. Okay. For non-rational functions, you find the so you could take the limit of it for infinity and see if it approaches a finite number. If it does, or if it's a finite number. If it is, then you have the horizontal asymptote. I guess, yeah. Yeah. Yep. Okay, so this is the Pythagorean identity. The reverse chain rule is the same as U substitution. We have a particular form of an integrand that we're able to use to integrate using the reverse chain rule. Okay, this identity, tan squared plus 1 equals secant squared. Okay, so this would be the tangent secant Pythagorean identity. This would be tan squared theta plus 1 equals secant squared theta. The cotangent cosecant, so this would be cotangent squared theta equals cosecant plus 1, or is it always? Okay, so it's always plus 1. I'm trying to figure out a way, or maybe a rule of thumb to remember. So for these two, we have the tangent and the secant, and then we have the cotangent and cosecant, I believe. Anyway, so for the left side, I have to remember the first one that I describe is going to be on the left side of the equation and is added by 1. So we'll go through that one again. Tangent secant, so that would be tangent squared theta plus 1 equals secant squared theta. Okay, I like it. What is the double angle formula for sine? So this would be sine squared theta equals 2 times sine square or sine theta and cosine theta. Okay, and I want to make sure that I have I want the reverse of this. Double angle formula. Double angle formula. The cotangent is cotangent squared theta plus 1 equals cosecant squared theta plus 1. Or sorry, so cosecant squared theta. Okay. Feeling decent about that. I think we'll just continue through those. I'm still... this may be in part due to this forum or this media is not great for practicing like procedural problems. I guess I could use the Excalidraw for walking through the problems, but I don't know. Maybe I could set up an additional camera so I get the... Yeah, maybe I set up an additional camera so I can show what I'm writing out on... Well, I guess I could just merely set it up so... yeah, I think we're fine. We'll just have to like set it up such that... actually, we'll need Anki. Such that it's... I think I just need to get better and feel more comfortable at doing this drawing using the Excalidraw for solving problems. I think that is the issue. Okay, so I'm gonna bring up this add thing here. I'll bring this guy over. Okay, and then we will just do this real quick. Okay. Perfect. Okay, so I think we'll just keep going on. I think we have okay. So right here, so we've done the main identity. So we will delete that. We got the double angle formula. Let's see if there's variations of the double angle formula. Variations of the double angle formula that are common. Okay, yes. I think I'm going to hold off on the other variations of the double angle, or sorry, yeah, of the double angle formula. I think we're good there. Reciprocal, and quotient identities. Oh, that's really tiny. Okay. Between 6 basic trigonometric functions, they arise from the definitions, blah, blah, blah. Okay, so these identities define 3 trigonometric functions as the reciprocals of the other 3. Okay. Secant. Okay. These identities express the tangent and cotangent functions as quotients or ratios of the sine and cosine functions. Okay, so I think we'll go ahead and just grab these. What is the... so we'll do... What is cosecant reciprocal identity? We have the cosecant, secant, and cotangent. So for these, the emphasis or focus of the reciprocal identities is to describe these. Well, I guess these aren't like. How would I say? When I first learned trigonometry, we only did cosine, sine, and tangent, and so these reciprocal identities are to define, or I guess the focus is on these, the 3 ones that are used less. And I think obviously they define the relationship between like the cosine and cosecant, the sine and the cosecant and the secant and the cosine, and the cotangent and the tangent. So describing yeah, as the reciprocals of the other 3. Okay. Taking. Okay. So that one. Okay. I do not like that. I'm going to. Oh, I'm actually going to go here for grok. I feel like we get better readout usually. Okay. Oh. Trigonometry. Oh. Trigonometry and math. And I'd like to have this one reverse as well. Okay. This identity. cosecant reciprocal identity. Okay. Then we're also going to do cotangent here. And cosecant. What? Oh, secant. That's the one I'm missing. Okay, I don't think I added the reverse for these other ones, so I'm just going to browse and make sure we grab that. New. Okay, perfect. Okay. So after the reciprocal, the quotient identities, what is the tangent quotient identity? They identify, these express the tangent and cotangent functions as quotients or ratios of the sine and cosine functions. Okay, that's great. Perfect. So what is the cosine, or sorry, what is the tangent? Tangent quotient identity. Okay. Perfect. Okay, so far, let's just like wrap this up. So we have the two angle identities. Sorry, we have the two angle. Yeah, probably identity is the best way to say it. Two angle identity. We have the Pythagorean identity of the main one, as well as the two variations, and now we have the reciprocal identities, which relate the reciprocal trigonometric functions, including secant, cosecant, and cotangent, to the other ones. And then we also have these quotient identities, which relate cotangent and tangent, and cosine and sine. Perfect. And so all these will be useful in the context of simplifying these expressions. And I've already done that one. What is the cotangent? And I think I actually might have still not had. Perfect. Oh. Okay, so the way I'll remember this is for the cotangent quotient identity. Cotangent starts with C and cosine starts with C, and they're both on the top. Okay, and the reason why I'm having the the language to be like a particular style is because I'm wanting to have it be reversible. So, yeah, that's the reasoning there. Okay, perfect. Maybe I'll move up. No. Yeah, this is fine over here. Okay, perfect. So, reciprocal and quotient identities. Describe the core trigonometric functions and their definitions. I also want to zoom that in as well. So it's giving me some optional Anki cards. Okay. So we will merely put these in. That did not work. Yeah, I wonder why this isn't working. It must be that there is some flag or some like a metadata or something that's coming over, because sometimes it likes it and sometimes it does not. So I'm not sure. So also I want to ensure that they're reversible, meaning we could have the question and guess the answer, or get the answer and guess the concept that it is the question. The key is not to have the important the name of the thing we're questioning. Have a question about in the answer. Okay. Okay, could you adjust the question such that they ask what the trigonometric function is? When the card is reversible, it means you could gain benefit from seeing it either way. Meaning, we aren't adding additional questions. It is merely about the form of the question and answer such that they are suitable for being shown in either direction. No. Oh my gosh. Please don't put bro, every time I've done the reverse card format, like regardless of the language model that is used, they do not understand what is going on. Like this has been like consistently the like most difficult thing that they've attempted to understand when I've worked with them for freaking doing this sort of exercise with learning. Like this is ridiculous. So like, bro, oh my gosh. Lamau, that's awful. It's awful. And it's been like I had this. Maybe this wasn't clear, but literally we received pretty much the same thing we saw before. So, okay. I just need to give some examples. Oh no, because like when I ask it, it's already so close to it, so I might as well just. Okay. Oh. I am always forgetting to add the yes thing for. So we need a yes. Okay. Now we need tangent. Okay, and now we need cotangent. Okay. We need secant and cosecant. And secant, if I'm recalling, is the inverse of the, I don't know about inverse, but the reciprocal maybe of the cosine, and cosecant is the reciprocal of the sine. Let's see if that's correct. 1 over cosine for secant. Okay, yeah, that's correct. Okay, and now we want the definition of the cosecant. And rip me, I only have... Oh, did I forget to do that? Reverse for that one. Okay. Okay, I'm going to go back to this to make sure I did the reverse for all of them. Okay, that one. Okay. Perfect. Okay. Then I have ranges for the trigonometric functions. I don't know how much I care about this. Yeah, I'm not sure. Okay, we're gonna see, oh, actually, I don't know if I have any more here. We'll go to ChatGPT. Could you tell me about the ranges for the trigonometric functions, as well as the standard antiderivatives for those functions, and also walk through how I take integrals when I can't use the power rule? Chicken and metric. Lamau. Okay, this is a good question. When are we in calculus? Calculus. When are you not able to use the power rule? To restate, so you can't use the power rule when the exponent is -1. Also doesn't apply to functions that are simply or aren't simple powers of x, like trig, exponential, or log functions. I don't like this answer. We are just going to open up a new window. I think it's using too much of the context to for that, but I'd like it to be more fresh. Okay. Okay, this one is much more clear. Oh, what the? Well, actually, let's see. Okay. And we're going to do calculus. Okay, let's see. I'm not sure what it means for this over here. Clear. It might have been a formatting issue. The ln? Natural logarithm. Wow, I never knew it was ln for natural logarithm. Interesting. Okay, I think I'm just gonna grab what I feel to be the most important ones. When taking standard antiderivatives of trig functions, you have plus c here. Is there anything needed in the context of that, or am I merely bringing the constant over from the previous one? Actually, no, that's not correct. Could you tell me more about the plus c that you add to the standard? Oh, I said antiderivatives. Okay, no, that makes sense. Because these are the standard antiderivatives. That's fine. Okay. Okay. No, that makes sense. Could you walk through the standard derivatives of trig functions as well? Da-da-da. Okay, I like this. I like this a lot. Okay. So I think I'll probably capture the standard antiderivatives and derivatives for functions. And then I think this one is fine to go, and that one is fine to go. Okay. Okay, I think we're going to do that, and then we'll see how far we can continue on the test. We may have to bounce back, but yeah, I think we're going to be looking better than we have been. Yeah. Just go to the bathroom real quick, I think. Okay. Okay, but these standard derivatives will be good to know, because these standard derivatives will be good to know, as I think I will need to do some transformations and like interactions with the things that I've been working with to get them done. I guess, for this one, we do see like here. Oh, we will need to learn about Riemann sums as well. Or Riemann sums, I don't know how it's said. Okay, so let's go back to here. Okay, so if this is the derivative, if this is the derivative of sine, then it follows that cosine's integral is sine of x, which I believe is correct. Okay, yep, but we just have this plus c. Oh my heavens. I hate the way that does this, like, duplicates it. I'm not sure why. So I think we'll just type these out. It's probably the quickest way to do that. And I think I'll do integrals and derivatives as well. Integral antiderivative. Antiderivative of cosine of x sine of x. Derivative of cosine of x negative sine of x. That would be cosine of x. Okay, what is the derivative of tangent of x? Secant squared x, where cosine of x is not equal to 0. I don't know if I care to do the remaining functions. Okay, I think if we run into an issue, then we will resolve it. But I think I feel fine there. Okay, let's see. Now we'll head back to the exam. Okay. 3 part. No, so this is 2 part 3. 2 part 3. Find the limit if it exists. If it doesn't, explain why. Okay. So, oops. So analyzing this function, see that the leading coefficient is 2. Or sorry, the leading coefficients power is 2, where below it is I guess it'd be 1. Since we are taking infinity, since we're taking the limit to infinity, oh wait, sorry. Okay, I'm actually on the wrong one. I'm not sure if this was correct. So let's double check that this is correct. If I'm recalling. Oh my heavens, that's not what I wanted. Copy. Yeah. Let's check if this is correct first. So I feel like I recall it not being, or possibly not being. Well, actually, I don't know if I checked this. I guess that's what it is to say. Okay, that will not translate well. We're going to go back and we'll just do a little snip. So here we're approximating. Okay, so this language about the leading coefficient does not work for the linear denominators. So we only use it in the context of quadratic or polynomials where the leading term has a power. Okay, that's fine. It's good to know. Is leading coefficient. Okay. Okay, this when we approximate bringing this function to infinity, we get 2x over negative 2x as we approach a positive infinity. We will approach negative infinity. Because we approach infinity, negative infinity, and infinity, as we take the limit of positive infinity, demonstrates that we don't have a limit, that this limit doesn't exist. Limit doesn't exist. Okay, I don't know if that's the best way to say it, but we'll see that. In a finite sense, okay. Okay. Perfect. And because the domain of sine is from -1 to 1, this is just going to have like an inconsequential effect on the nature of the denominator. So that's why we can just yeet it out. Okay, so I'd say that was good enough to go to the next one. So for this one, the limit... Take the limit of x squared cosine 1 over x, and we're taking the limit to 0. So 0 squared equals 0, but 1 over 0 and for the cosine does not exist. So that is not great there. So because we can't take, because this is undefined, 1 over 0, then we have an issue there. Okay, I think we'll do some, let's see, let's just do some exploration to see if we can adjust things such that we have something nicer here. So we know that the cosine is equal to 1 over the cosecant of x. Oh, shoot. But the issue is, and that actually doesn't help us. So if we know that, yes. If we know the cosine is of x is equal to 1 over the secant of x, I was thinking, oh, maybe this will help us. But the issue is that our x right here is equal to 1 over x. So even if we bump this down to the bottom here, we're still going to have the secant of 1 over x. So we're actually not helped in that sense for the situation. Okay, what other approaches could we use? Um, um, okay, so now I think we take the limit for us approaching 0 from the left and right side, because the limit can, I believe the limit can still exist if those equal each other. So I guess the big issue we have here is that, let's see. So as cosine, let's see, calculator. Do we have a cosine here? Okay, so we'll do the cosine of like, okay, so as the cosine gets arbitrarily large, we're going to approach 0. Oh, okay. Oh, interesting. Okay, so as this gets arbitrarily large, we're going to approach 0. And I think it's, yeah, and also the case that if we approach, we're going to approach 0 this way, right? Okay. And being that we're approaching 0 from either way, this is like, so we approach 0 from the left side or the right side. Oh, let's see. Oh, no, wait a second. That's incorrect. What am I saying? Oh, no, that is correct. Yeah, because as I get a smaller and smaller number here, my overall number is going to be higher and higher, right? And so, and as I approach 0 here, either in the negative or positive direction, I'm actually going to result in, I'm going to result in us also getting arbitrarily close to 0. And so I think from either direction, like we're always going to evaluate, yeah, I think the limit exists for 0. Well, I guess it depends. I need to recall this, because if it's, yeah, I believe it's the case that for a limit, if we take the limit from the left and right side and they're equal, even if the limit doesn't exist for like a given point, then we still, I would say, the limit exists for this function, this function and is 0. If we attempt to plug in 0, we will get undefined. However, as we get arbitrarily close to 0 from the left and right directions, we converge on the same value. Therefore, the limit of this function, taken function, taken at 0. Okay, I'm feeling all right about that. Let's see if I'm wrong. We're going to take another snip. Okay, so I have the right idea here. Could you describe what portions of my answer, oops, could be tightened up more? So it looks like instead we're using the squeeze theorem. So maybe what we're looking at here is also explain the steps explicitly for how one would evaluate this limit. Okay, so I correctly identified limit exists. I mentioned it's approaching from both sides, which is important for confirming the limit. If we attempt to plug in 0, it will get undefined. This is partially misleading, as cosine is undefined at 0, but x squared is defined. So technically the entire expression is undefined at x equals 0, but you're not plugging in for a limit. You're observing the behavior as x approaches 0. As we arbitrarily get close to 0 from the left and right direction, we converge on the same value, 0. This isn't quite accurate because cosine x does not converge at all. It oscillates wildly. So we can't say the expression converges in a traditional sense, and say we rely on the fact that oscillations are dampened by x squared. Okay, I like that. I think that's much better, yeah. So the limit exists and equals 0, while cosine of 1 over x does not approach a single value, x equals 0, or x to the limit of 0. It stays bounded within negative 1 and 1. Since x squared equals 0, the product is squeezed between negative x squared and x squared both go to 0. By the squeeze theorem, the limit is 0. Okay. Interesting. Okay. So recognize that it oscillates as x approaches 0, but is bounded. Take the limit of both bounding functions. Apply the squeeze theorem. Okay, that's cool. Okay, so in this sense, we're using the squeeze theorem for trying to find. Okay, interesting. So, when I learned about the squeeze theorem initially, I thought it was odd because it seemed to be a unique case when we'd have like 3 different functions, and we'd be able to take the functions of the or we'd be able to take the like external functions, Yeah, so that just seemed like odd to me. But yeah, this makes sense. Because we know that. Okay, so looks like the squeeze theorem is used in the context of like finding limits. And this is we find the upper limit and the lower limit, or sorry, we analyze the limit from the left and right side. Okay. Coming back to the previous question or the previous response you gave, you use the squeeze theorem. Could you walk me through the intuition for applying it such that we have negative x squared is less than or equal to x squared times cosine of 1 over x is less than or equal to x squared? Could you describe the like intuitive steps you would take to understand that you're wanting to pull out negative x squared, and those are the lower and upper functions respectively? Okay, so we know this the oscillation, and it doesn't converge, okay? So we can't find the limit directly by substitution or standard limit rules, okay? But we know something, okay. It never goes beyond those bounds. It gives us a bounded part of the expression, okay. We multiply the bounds by the other parts of the expression. Oh, that's interesting. Okay, so this is a whole different way to think about. So it's, oh, okay. So we use the squeeze theorem for bounded ones. Interesting. Okay, so it looks like for the squeeze theorem, we are able to use it in the context of functions that are bounded. Is that correct? Exactly. Okay. That's so interesting. Wow. Okay. How? And in what situations? Okay, maybe I already have this captured for the squeeze theorem. Squeeze, wheeze. Is used to find the limit of a function by squeezing between two other functions whose limit are known or equal to the point of interest. If the outer functions approach the same limit. Okay, so I need to know when we should apply the squeeze theorem. In what situations do we apply the squeeze theorem? Less than 50 words. Applies the squeeze theorem when a function is difficult to evaluate directly but is bounded between two simpler functions that converge on the same limit. It's especially useful when dealing with oscillating functions. Okay. Okay, let's see. Okay. Okay, and then in the context of applying the squeeze theorem, or sorry, in the context of bounded functions, or how, what does applying the squeeze theorem look like in the context of working with bounded, with a function that has a component that's bounded? That is bounded, as in our example above, as in this question, as in the example above. Okay. Okay. Feeling good about that. Okay. So in the context of the example that, or question that I gave earlier, where we talked about the squeeze theorem, in order to get full points on a question for this, I would probably have to reference the squeeze theorem, correct? Question mark? Or would my previous example be, or sorry, previous answer? Or would my previous answer be sufficient? No, that's fine. Could you give me some intuition for what is sufficient justification for finding the limits? Right now, I have like an intuitive grasp of how limits are found, but don't have the correct understanding of what would be needed for formal justification. Could you give the cases in which, or the nature or the different natures by which we could have a formal justification of a limit, or different contexts? I don't know. Okay. So we have direct substitution, algebraic simplification, and squeeze theorem. And we have the limit laws or derivative limits. Use L'Hopital's rule. Okay. Sweet. So we're approaching 44 now. I think we'll probably just end at 45. So I'm gonna capture this, and the next step will be reevaluate my answer in this context. Okay, I think we made reasonable progress today. Yeah, I think that was good. Perfect. We'll see you guys on Monday.